Okay, we are going to solve a fairly complex problem, a gas turbine problem with a regenerator in it. It's problem number 8116 from the problem module. So let's see what are the information given to us. The air enters the cycle. This is the atmospheric condition, that's state 1, given to us completely. Mass flow rate is also given. So if we may write about state 1, we can already build up our state 1. Pressure is known, temperature is known, and mass flow rate is known. Okay, so let's see what other information are available. The pressure ratio is 10, which means P2 over P1 is 10, so we know P2, which must be equal to P5, P3, etc. The turbine inlet temperature is given to us, and regenerator efficiency is also supplied. We are supposed to find the thermal efficiency of the cycle and do a what-if scenario. We'll come back to this later. Let's make the problem even more complicated. Complicated by slapping in a compressor efficiency. Let's say compressor has an efficiency of 90%. So to tackle this problem, we have to renumber the states, because now we will have an ideal state. Says 2 is our ideal compressor exit state, and 3 is the actual compressor exit state, which means all other states has to be shifted by 1. 3 becomes 4, 4 becomes 5, etc. Now let's set out to find all the states and the compressor power, turbine power, heat inlet, heat input, heat rejected, etc. from the cycle. So let's begin with state 2. Let's quickly draw a TS diagram of the compressor. And we recognize that state 2 will be isentropic to state 1. The pressure at state 2 is 10 times 100. T2 over T1, we can use the isentropic relationship for perfect gas, which we have been doing quite a bit in all other problems. So therefore T2 can be obtained now. T1 is already given, 290, 10 to the 1.4 minus 1 divided by 1.4. And if we can calculate that, we will get T2 to be equals 560 Kelvin. Okay, how about T3 now? T3 is what? The actual turbine exit, compressor exit. It will be to the right of state 2. So this is 100 kPa line, and this is your 1000 kPa line. So to find state 3, we have to use the compressor efficiency. What is the definition of the compressor efficiency? The ideal compressor power, which is m dot H2 minus H1 divided by actual compressor power, which is bigger, H3 minus H1. And that simplifies to T2 minus T1. CP gets cancelled in the PG model. And because compressor efficiency is supplied 0.9 times T3 minus T1. So that gives us T3 equals T1 plus 0.9. Notice that this equation is valid only for the PG model. Whereas until this point we did not use any model, so this will be valid for also IG model. So this will give us H3 equals H1 plus H2 minus H1 divided by eta C. So this is a stronger relationship between 3 and 1 and 2, because this will work for any model, whether it's PG model or IG model or even PC model in the future. Anyway, to solve the problem manually, we will use this relationship for the PG model. T1 is known, T2 is known, T1 is known. So plugging them in, we get T3 equals, if you do the calculation, you'll get 590, approximately 590 Kelvin. Well, now that we know T3 and T1, we can quickly determine the compressor power. The compressor power will be simply m dot Cp T3 minus T1, 6 kg per second, 1.005, and T3 minus T1 are how much? Our T3 is 590 and T1 is 290, and that produces approximately a power of 1808 kilowatt. Okay, so let's go and verify that using a test calc. So we launch open steady test calc, going to the specific branch. We go down to vapor power and gas power cycle and select the PG model and click test calc to launch it. Okay, so let's enter our state 1. We first select gas, which is air, 100 kPa and 290 Kelvin, 6 kg per second mass flow rate. Fairly simple. Kinetic and potential energy are set to 0. Velocity is 0, z is 0. State 2, we have the pressure 10 times P1, and it's isentropic to state 1. And the mass flow rate is the same, so state 2 is determined. Now to find state 3, which is the actual turbine, actual compressor exit state, P3 equals P2, pressure remains the same at the actual exit. However, the enthalpy, we can connect enthalpy at H3 with the relationship that we developed. If we go back, and this is what we got, H3 equals H1 plus H2 minus H1 divided by compressor efficiency. So we'll go back and substitute it here. H3 equals H1 plus H2 minus H1 in parenthesis divided by 0.9, which is the compressor efficiency. And of course, the mass flow rate m dot 1 remains the same. So we got a calculation, yes, we got the same answer as manual answer, but to verify, to check the consistency, what we should do is do a TS diagram, draw the constant pressure line by clicking on the P equals constant button, and then we can see that 2 and 3 must be on the same pressure line, the 1000 kPa line, and state 1 should be on a different pressure line, the 100 kPa line. So this is your 100 kPa line, and this is your 1000 kPa line, and 2 and 3 has to be together on the same, on the same line, And 3 has to be a little bit to the right of 2 because entropy at 3 is a little bit higher than entropy at 2 because of internal friction in the compressor. Okay, to calculate the compressor power, we go to the device panel. State 1 is the compressor inlet and state 3 is the actual compressor exit. State 2, remember, is only for the isentropic compressor, which doesn't exist, which is just a benchmark to compare with. Okay, so enter adiabatic condition, Q dot equals 0, and we calculate the compressor power to be 1807, which is what we calculated, approximately the same number here. Okay, let's keep on moving. Now we'll go to let's jump to state 4. So to do state 4 and 5, just to put it in perspective of the TS diagram, so we have state 4 here and state 5 here. For state 4, everything is supplied to us. Pressure equals same as P3, which is 1000 kPa, and temperature is given to us 1500 Kelvin, the maximum temperature of the cycle. 4 and 5 is isentropic. In the isentropic condition can be applied again. So therefore T4 divided by T5, P4 divided by P5, K minus 1 over K, which means T5 equals T4 divided by, now P4 over P5 is what? P4 over P5, this is a 1000 kPa line, this is a 100 kPa line, so this is 10. Solving this, we obtain T5 as 776 Kelvin. So we can easily obtain the turbine power H4 minus H5, and for PG model it becomes CPT4 minus T5 times m dot. Substituting the numbers, we got 6, 1.005, T4 is 1500, 776, and the turbine power is about 4347 kilowatt. Okay, so let us go and check if the answer holds up when we verify with test calc. State 4, pressure equals P3 and temperature equals 1500 Kelvin. This is the turbine inlet conditions. Very simple, equals m dot 1. And state 5, pressure at 5 equals same as pressure at 1, because at the exit of the turbine the pressure is atmospheric. Mass flow rate is the same, and entropy at 5 equals entropy at 4, isentropic condition in the turbine. And we find the turbine temperature that kind of matches with what we found. Let's find the turbine work. Let's call it device B. Turbine inlet is state 4 and turbine exit is state 5. No heat transfer, and work is calculated to be 4356. Just to make sure, let's do a TS diagram again. If TS is already selected, if you click the calculate button, the graph will show up. Constant pressure lines, again it makes sense. 4 to 5 should be isentropic, 4 and 5 are vertically aligned as expected. Okay, now let's start the task of calculating the internal states, the other states, 6 and 7. No, 5, 6 and 7. Okay, so we go back to the PowerPoint. Okay, so to find the next state, that is, let's say state 6, we have to understand what is the regeneration efficiency. What does regenerator effectiveness means? Well, look at what happens in a regenerator. The compressed air is heated from state 3 to state 6 by the hot exhaust from the turbine at state 5. So state 5 is the hottest temperature. So how hot can the compressed air get? The answer is at the most to temperature at 5. That's the hottest temperature. But in any real regeneration system, T6 will be slightly lower than T5. So the effectiveness is defined as the rise in temperature of the compressed gas, which is T6 minus T3, divided by the maximum possible rise. And we understand, because 5 is the hottest gas that enters the regenerator, T5 is the highest temperature we could have gotten in a perfect regeneration system. So this is the definition of a regenerator. So therefore, using this equation, we can easily get T6. T6 will be, if we manipulate this equation, it will be T3 plus 0.7 times T5 minus T3. Okay, so we'll go out and write that equation in another page. So we are trying to find state 6. Obviously, it has the same pressure as P3. There is no pressure loss in the heat exchanger, and the temperature T6 is given by T3 plus the effectiveness times T5 minus T3, and we already know all these values. T3 was calculated as 560 and T5 was 776. And solving that, we get a T6 of about 711. So notice 776 could be the highest temperature we could have ever reached. Instead, we reached 711 K. Not bad. If we want to verify that using test calc, we'll just go and substitute this equation there, T3 plus 0.7. So let's go calculate state 6. Pressure equals P3 and T6 equals T3 plus 0.7 star T5 minus T3. And of course, mass flow rate hasn't changed. It's the same mass that passes through each device. And to know what T6 we calculated, park the pointer on T6, and you can see the value appears at the top panel, 720.6 Kelvin. So that seems a little bit different. Let's check the answers again. In fact, indeed, what we did wrong, if you notice, T3 is not 560, it is 590. Had we put the correct value here, T6 would have been 720.6. So that's the value of verification. Look, the formula was correct. While substituting T3, I put in the value of T2 by mistake. T3 is 590, whereas T2 was 560. Okay, so now it's time to go and calculate the last state, the state 7. We have found all the states. So how do you find state 7? Well, to find state 7, concentrate on the regenerator. If we do an energy balance on the regenerator, that will give us the unknown, because we know state 2, state 6, and state 5. The easiest way to do a heat balance on a heat exchanger is to think like there is a fluid which is donor, which is giving out heat, another fluid which is receiver, receiving the heat. As you can understand by looking at this diagram, the hot gas from the turbine exhaust is the donor going from 5 to 7, and the compressed air from the compressor is gainer or receiver from 3 to 6. So the heat received by the compressed air is what? M dot H6 minus H3. So M dot H6 minus H, so let's do a heat exchanger analysis. So to find state 7 energy balance, we apply an energy balance on the regenerator, which is just a heat exchanger. So the heat that is picked up by the compressor is M dot H6 minus H3, and the heat, so this is heat gained by one fluid, and the turbine exhaust is at 5, and after the regeneration it is 7. So this is the heat lost by the hot fluid. Heat gained by the cold fluid must be equals heat lost by the hot fluid, and that gives us a formula for enthalpy. If we want, we can get a formula for enthalpy or temperature by substituting the PG model. So if we get both the formulas, for the enthalpy the formula will be H7 equals H5 minus H6 plus H3, and if we do for temperature, it should be T5 minus T6 plus T3. Substituting this number, T5 is 776, T6 is 711, and T3 is 590. And that gives us a T7 of 655. Okay, let's verify. We'll use this equation because this is more general. It can be applied to ideal gas model. 5 minus 6 plus 3. So you go back. Enthalpy will be 5 minus H6 plus H3, and the pressure at 7 equals pressure at 5, which is equals 1, of course, 100 kPa and 6 kg per second. So this gives us a value of 646, not quite what we got. So let's see what mistake we made again. Okay, so we used a value of T6, which we calculated to be 720. Oh, so again we substituted the old value, the wrong value. It should have been 720, and then we would have gotten exactly what the test calc is telling us, 646. Again, we made the same mistake. We substituted a bad value for T6 here. So now we have calculated all the states. we can now easily calculate what is q dot w dot net and what is q dot in. W dot net is turbine work minus compressor work, and we can, so the net work is given by the difference between W dot T, which is 4357 or 56, and the compressor work, which is about 1808, and the net work becomes 43, the network becomes 2549 kilowatt. So how do you calculate Q dot in? Because we need that to find the efficiency. Q dot in, you recall, if you go back to the diagram, where is the Q dot in taking place? In the combustion chamber between 6 and 4. So it's m dot H4 minus H6. M dot six Cp T4 minus T6, and if we substitute T4 and T6, and T6 is 590 if you recall, and then we get 4693, approximately 4693 kilowatt. So therefore the thermal efficiency is calculated. It is W dot net, what we pay for, and that turns out to be 0.543. But typically thermal efficiency is given in percent term, 54.3%. To verify that, in the using test calc, you have to complete all the devices to complete the cycle. Otherwise the cycle panel will not make any sense. So we have only calculated 2 devices, A and B. So let's go ahead and see how we calculate all the other devices. So let's say device C. So recall that device A was compressor, device B was the turbine. So let's do device C between 6 and 4, the combustion chamber. So state 4, state 6, sorry, is the inlet, state 6 is the exit to the regenerator, and state 4 is the turbine inlet. So this is the inlet to the combustion, state 6, this is the exit to the combustion, state 4. There is no work transfer. So 4692, this is the heat transfer in the combustion chamber. So essentially we are verifying Q dot in. So this is the number we just got. But still we have 2 more devices. One is the regenerator and another is the heat exchanger to get back the air back to state 1. So let's do the regenerator, state device D. What do we have in device D? In the regeneration system, state, if you recall, if you look at the diagram, you can consider 3 and 5 as entering, and state 3 enters and comes out as state 6, and state 5 enters and comes out as state 7. And a regenerator is a non-mixing device. So it's important that you understand what I'm doing here. So look, the diagram, if you look at the diagram, it changes. If it's a mixing device, it assumes the state 3 and 5 comes and the gases mix here, goes out at 7 and 6. But this is not what a heat exchanger is. the hot gas, the cold gas is from 3 to 6, and hot gas goes from 5 to 7. As you can see, they are not mixing, they are just exchanging heat. And there is no work transfer, of course, and there should be no heat transfer either because it's insulated. So I'm doing an overall analysis of the heat exchanger where we are looking at the entire device. There are 2 inlets and 2 exits, and of course we expect there should be no heat transfer if we correctly have calculated all the states. We have not finished. There is a last device we must have so that the cycle is complete. And what is that last device? The last device is the heat exchanger that we need to take gases at state 6 or gases at state 7 really, which is exhausting to the atmosphere, back to state 1. And for that, there is no work transfer, and we get the Q dot out here. Now if you go to the cycle panel and do a calculate, it should calculate all the quantities that we discussed, including the thermal efficiency to be 54.3%, and which is exactly what we got manually. Finally, suppose the what if scenario. Look how simple it is to change a parameter and redo all the calculations. First of all, if you just click the button super calculate, all it does is goes back through all the calculation, iterates through them, and it produces test code which you can copy and paste and save it for later use. You can then come back and paste it here and click the load button, and it will instantly run the entire case. Also in the output you can see all the detailed output of all the states, all the devices, etc. So suppose our task at hand is what happens if the regenerator become more efficient. It's right now 70% effective, so let's make it 100% effective. So where does the regenerator appear? If you recall, it's at state 6. So look, the 70% efficiency appears here. So if we simply change that to 100% by changing 0.7 to 1, we calculate the state, and the way it works, if we now click a super calculate button, all the states will be recalculated, and we can go back to the cycle panel and pick the answer. See, the efficiency has increased to 58.5%. So if you go back, write down for effectiveness of 1 becomes, how much was it? 58.5%. Now suppose, okay, let's go back to the original problem, 0.7. So the original efficiency was, remember, 54.3%. So we are back to the original problem. Now suppose we say, instead of the regenerator, suppose the compressor suddenly becomes very efficient. Where did the compressor efficiency go? Remember, recall that when you calculated state 3, we entered the compressor efficiency here to be 90%. Suppose compressor efficiency is 100%, 1. Now if we do a super calculate, let's see how much it impacts the cycle, 57.5%. So look, $57.5. Efficiencies of the regenerator matters, efficiency of the compressor matters. You can see that we can get substantial increase in the thermal efficiency if the components are efficient. So you can see the potential for doing a number of parametric studies in a class ME555, and the entire class is spent on this kind of parametric study. Hope this kind of problem will excite you to come back and do a complete analytical and numerical study on problems of your interest.